Now we know the electric potential of a single charge. We can expand our knowledge. So if we have lots and lots of discrete charges, they all have different spatial location. All you have to do at any observation point is to sum them up. The procedure is identical to what we covered for E field intensity. But the only difference, if you compare finding the potential, total potential, due to discrete charge distributions, as compared to the same charge distributions, but you're trying to find the E field intensity. For E field intensity, you are analyzing vectors. So you have positions and you have a more complicated spatial dependence. Right? Look at the potential. It's a scalar. So the only thing that matters is the distance and the sign of the charge. Right? So the conclusion is, for the same problem, well, finding electric potential is easier because you're only dealing with scalars. If you were to find E field intensities, you're dealing with vectors. Okay, more difficult. All right, so we can expand from discrete charges to continuous charge distributions. That's also fine. For potential, all we have to do is we expand from summation to integration. If you have volume charge distribution, surface charge distribution, line charge distribution, really doesn't matter. All you do is sum them up. If you really have continuous distributions, you perform integration. You have discrete charge distributions, you just perform summation, right? So this is a general guideline. Eventually, if you want to understand everything, ideally, we need to understand the E field intensity, right? It's a vector. But somehow, up to now, we have learned at least, well, 3 methods to find out the E field intensity. The easiest one is given by Gauss's law. So in the future, whenever you receive a problem or you want to study a certain case, if Gauss's law, right, you only have to form a closed surface and you count for how many charges you have within that closed surface. That's what Gauss's law tells you. So whenever you have good symmetry, you can find a way to form a simple closed surface. Use Gauss's law to find out the resulting in E field intensity. If your problem does not give you a lot of easy access to symmetry, the easier way is find the scalar electric potential first. Why? Take a look. Finding the potential is usually much, much easier as compared to finding the vector E field intensity. Okay? So what I'm proposing is, if you cannot or you don't know how to invoke Gauss's law, for sure, try instead to find the electric potential. Being a scalar is easier to analyze. You have less chance to screw up. Right? So once you have derived the scalar electric potential as a function of space, then you perform its gradient. And remember, please remember to add the negative sign. And then you have the proper expression for the electric field intensity. Okay? So the strategy is, if you can use Gauss's law, use it. If you cannot, you're not certain, trying to calculate the potentials instead. It's like a byproduct. Easier, but it can also give you the final result. So if in some cases you don't know how to invoke Gauss's law and you don't really know how to calculate the scalar electric potential, then just use Coulomb's law. Okay? That's your final strategy, your only way. Just do it starting from raw, step by step. Okay? Use Coulomb's law. But usually, if you don't know how to invoke this one and you don't know how to calculate this one, your certainty, your chances of getting this right is really not that high, right? Think about it. This is like philosophy. If you can use the easiest method, use it. If you cannot, use the second easiest and use the hardest. What are your chances of getting the right answer using the most difficult method? Low. Okay? Think about it. So, just try to convince you. I am going to walk you through a simple example. It's example 3-9 in your textbook. So we are going to calculate, well, eventually we want to know the E field intensity. But first, let's try to calculate the scalar electric potential first, and then perform this gradient. Alright? So now we have a uniform charge distribution in a disk. Okay, so charges are uniformly distributed over a disk. So you have rho s, which is a constant. It's not position dependent, right? Charges are uniformly distributed on this disk. And this problem wants to know, if I have an observer on the z-axis with certain distance, what is the resulting E field intensity? But first, let's try to look for the electric potential first, because potential is scalar function. Alright, always, before we begin, before you write down the equation, don't rush. As I mentioned time and time, over and over again, when you take a problem, the most important issue is you are being able to identify which one of the three orthogonal coordinate systems is most beneficial for you. In this case, the geometry we're trying to analyze is a disk, right? A disk. A disk can be most easily described using cylindrical coordinate system. Okay? So we want to use cylindrical coordinate system for this case. If we decided to use cylindrical coordinate system, then each differential surface in this case is pointing to what direction? This is the point where you really need to think. Currently, the problem is spelling out the differential surface for you, this field pink area. So this differential surface is actually pointing in the z direction, right? So your differential surface is the one pointing into the z direction, so dsz. As I mentioned repeatedly over and over, if your area is in the direction of z, then its magnitude its area must be determined by the differential length in r and phi directions. Okay? So this is again where you have to remember, in the phi direction, because your unit vector is an angle, so this differential length is in fact an arc length. So you have to have r defined. And again, I'm using the prime system to denote the charge coordinate. Okay? Alright, so the area is pointing in the positive z direction, but its magnitude, the area, is defined by dr prime times r d phi prime. Okay? For each differential surface, its center to my observation point, I must know its distance. And that distance is easy, right? This is 0, 0, z. The observation point is somewhere on the z-axis. So that distance is z, and this distance is r. So basically, r prime squared plus z squared, and you take the square root, and that is my proper expression for the distance. Right? Then we can just put into the integration form. Electric potential as a function of z, because I limited my observer to be on the z-axis. There is no x, no y allowed, only z allowed. Okay. So rho s divided by 4 pi epsilon 0, and then this is my r, my distance r, and this is my integration of the entire surface. It's a scalar treatment, much, much friendly as compared to vector analysis, right? Okay, so this phi, the azimuth angle, you have to integrate from 0 all the way to 2 pi. And luckily, in the integrand, we have no phi dependence. So that gives you a direct multiplication of 2 pi. Right? 2 pi. So all we have to integrate is in the radial direction from a radius of 0 all the way to b. The radius of this disk is b. Okay? So do you know how to perform this integration? I hope so. It's straightforward. Okay? So take a look. There's one small trick. One small trick. If you want to derive the proper answer, you have to note your observer can be anywhere on the z-axis. So this z value can be positive, meaning you're above the disk, but you can also be below the disk, where z is negative. So whenever you work on this problem, be careful. You have to take consideration into the z location, is the value being positive or negative. Okay? So why do I need to add this absolute value sign to z? Let's try to analyze this. If I draw the cross section, so this is my disk, and this is my z-axis. Okay? Somehow we know I have charge distributions, and I assume I have positive charges. So somehow, this is my potential. So the potential needs to decay, right? As I move away from the disk, the potential decays. Okay? If I move away in the direction along the positive z-axis, it decays. And what happens if I move along the negative z direction? I move away from the disk. It also decays, right? This should be symmetric. By that reason, you must have this minus and the absolute value. Otherwise, if you don't have the absolute value, when your z is negative, negative, negative becomes plus. So it means if you don't have the absolute value, your electric potential is increasing as you move away from the disk in the negative z direction. So that cannot be true, right? So although the mathematical derivation is simple and straightforward, you can just perform the integration, but in the end, you always need to understand the problem. In a physical sense, if you have the charges, you move away, you expect to have a decay in its electric potential. It has to decay when you move away in both directions. So how can you properly formulate that fact? Using math, you have to add this absolute value sign, right? Okay, so now we have the mathematical formulation for V is a scalar. We can perform its gradient and then add a negative sign to it to find the corresponding E field intensity of vector. So in this case, even though, so again, do you still remember the proper formulation for gradient in cylindrical coordinate? If not, go back and study because next Monday you will be using it. Right? In this case, we're lucky, we only have to perform the z differentiation because the entire scalar function is only z dependent. So you only have to perform the z differentiation. And for cylindrical coordinate, r and z, you're lucky, you don't have to add the Jacobians. Okay? So basically, you can just directly differentiate electric potential in the z direction. Right? Again, pay special attention to the directions. Okay? When you are above the disk, you have one way to express the resulting E field distribution. When you are below the disk, you have to make proper changes to truthfully reveal that the fact is, if you have positive charge distribution of rho s, then your E up and E down are having different directions, right? Field lines start from a positive charge that emit in a radiant pattern. So when you are above it, your direction is pointing up. When you are below it, being radiant, right, outward, you have to have a flipped sign. So that's a reason why when you're below it, you have a negative z pointing E field intensity. So the trick is, in dealing with electromagnetics, you have to understand about the signs of the potential, the directions of the fields. Alright? It's extremely crucial. An easier way to express this rather complicated result is you use a sign of z. Right? So where z is positive, this gives you positive 1. Z is negative, it's negative 1 to take account into that negative sign. right? Take a close look at our result. Well, you can take this one, right? Forget about the sign. Have we derived this previously? Is this entirely new? Do you still remember what we concluded in last class? If you have a planar charge distribution, do you still remember what type of E field intensity does it contribute to? It's a constant, right? If you still remember, if you have a planar charge distribution, it sets up an E field intensity which is constant, does not decay when you change your distance. So in this case, you have the distance dependence in this term, right? In the second term. But in the first term, you have 1. The first term is not distance dependent. So somehow this is telling you this disk geometry, when you make certain approximation, it will become the planar charge distribution that we analyzed. In that case, we assume the plane is infinitely large. Okay. So how can we make this disk with a finite radius to appear as infinitely large? Think about it. This is where my job really comes out. 2 seemingly different examples. But if you're willing to change and challenge yourselves, make approximations, the 2 problems become the same. So if the observation point, the z value, is very small, so you're trying to evaluate the E field intensity very close to the disk. When your z is very, very small, you're very close to the disk. This B relatively seems to be very big, right? So if your B to Z ratio is really huge, like beyond 10, 100, this term can be dropped. Why? Because B is much, much greater than Z. You don't care about this term, and because B is much, much greater than Z, you don't need to care about this term. So if B is reaching to infinity, or another sense, you are very close to this disk. Your E field is pointing in the Z direction, and you have the sign of Z to reflect its true direction, but the magnitude is rho s divided by 2 epsilon 0, which is identical to what we covered. Right? Do you want to go back to where we covered the disk? No, the plane. Do you still remember this one? Rho s divided by 2 epsilon 0. Identical. Right? So 2 seemingly different examples. If you're willing to challenge yourself and ask yourselves in certain extreme number, they become the same. Okay? Here you have derived using Gauss's law, so the E field intensity is pointing in the Z direction with the right direction included by the sign, but the magnitude is a constant, rho divided by 2 epsilon 0. Here you see the same thing. Even though you change the geometry of the charge distribution into a disk. But as long as you're very close to that disk appears like an infinitely large plane. Therefore, the answer should converge to what you have derived previously. And that is truthfully revealed here. So if B, the radius, is going to infinite, meaning you have a very big disk, the second term can be dropped, and your result converges to what we derived previously. Right? So I know time is not exactly up. We are 5 minutes early, but let's take a recess. So we take a 10 minutes rest, and we will come back to the analysis of electric dipole in more details. Right?